have a function f of x is equal to the square root of x plus 11. And now for the first part, we're looking at the determination of y is equal to f of x whenever x is set to 25. And looking at what we have with f of 25, okay, so now we're looking at the square root of x plus 11 to be transformed to the square root of 25 plus 11. All right, so now 25 plus 11 is 36. And the square root of 36, okay, we have is equal to 6. Okay, so we have for f of 25, okay, that is equal to 6. Okay, now for what we have in the case of f of negative 7, okay, so when x is negative 7, we're looking at what the y value is going to be. And so we have, working with the input, negative 7. So we have the y value is going to be the outcome whenever we have the square root of negative 7 plus 11. And minus 7 plus 11, okay, is going to be 4. And the square root of 4 reduces to only 2. Okay, so f of negative 7, okay, is equal to 2. Okay. Now, for what we have concerning the domain of this particular function, okay, and again, we have f of x equal to the square root of x plus 11. All right. Now we have the function given as an even root radical in direct terms and with even root expressions. Okay, now we can have f of x to be 0 since we're not looking at a fraction with this radical on the bottom. And we can have x plus 11 to be positive. Okay, and so since the only restriction is coming from this setup where f of x is an even root radical, again, x plus 11 cannot be negative. Again, it can be 0 and it can be positive. So if I set up what I have in terms of an inequality, okay, so we have x plus 11 is greater than or equal to 0, and in solving for x, okay, and we're going to have the function to be defined, okay, as long as x is greater than or equal to negative 11. Okay. And just sort of a visual. Again, in terms of domain, you don't have to graph, but it can provide, once again, a bit of hands-on approach. Okay, and so we have x equals negative 11 as part of the solution. So we have a solid point. Everything else will be greater than. And so we're going to have a ray that is going to go out to the right. And we have running continuously out in the direction of infinity. All right. And so we have for the domain, okay, if we display the result in interval notation, we're going to have the lower limit to go from and including negative 11. Okay, so we're going to have the bracket around negative 11, and then we have going continuously out to infinity. And again, infinities are boundless, and so they will stay in the parentheses. All right. Now, for what we have in the case of the next function, okay, so we have a bit of a synthesis of an even root radical as well as a rational expression. And here we have, for this one, we have f of x is given as x minus 3 all over the square root of x minus 4. And looking at what we have for this function, whenever we have that x is set equal to 5, okay, so we have for part A, okay, we have in the case of f of 5, okay, so have 5 in place of x, so have 5 minus 3 all over the square root of 5 minus 4. And we have 5 minus 3 is 2, and the square root of 5 minus 4 is going to be the square root of 1. And again, the square root of an expression cannot reduce to a negative constant. So while two numbers, negative and positive 1, will square into 1, we have the square root of 1 is only at 1. And so we have 2 over 1 comes out to 2. So for the graph of this function, whenever the input x is set to 5, we have the corresponding y value is equal to 2. Okay. Now, in changing up the input, okay, as we go from x is equal to 5 to x is equal to 9, and for this one, okay, so for f of 9, so we have 9 to represent x, so we have 9 minus 3 all over the square root of 9 minus 4. Okay, so we have 9 minus 3 is 6, and the square root of 9 minus 4, okay, this will be the square root of 5. And you can leave this result as it is, okay, with the square root on the bottom. And I'll show you just sort of another version. And this would be like if you were to take Math 172 and you wanted to take care of the radicals on the bottom. What you would do here is that you would take 6 over the square root of 5 and multiply by 1 in the form of the denominator over itself. And for this version, okay, so this would be 6 times the square root of 5, and the square root of 5 times itself, this would be the square root of 25, and that would go to 5. So again, either version of this answer comes out to the same result. All right. Now, for what we have in the case of the determination of the domain, again we have with f of x equal to x minus 3 all over the square root of x minus 4. Okay, now again the burden in terms of where the restrictions will be placed will be upon x minus 4. Now x minus 3 is okay. Okay, you don't have an even root radical in the numerator, and plus you can have a 0 numerator as long as you do not have a 0 denominator. Okay, so everything is in terms of the restrictions will be riding upon x minus 4. So here we're going to have a twofold restriction. First of all, okay, because we have x minus 4 inside the square root. Okay, we have x minus 4 can't be negative. And because we have x minus 4 in the denominator, okay, so we have the x minus 4 cannot be 0 either. Again, just sort of going back now, before we had an even root radical expression. Now we had x plus 11 could be 0, and the reason for this again is that we don't have a fraction with the square root of x plus 11 on the bottom. But now with the square root of x minus 4 is situated on the bottom, so there is that added restriction that x minus 4 cannot be 0. So again, this means that the nature of the inequality is going to change where x minus 4 must be positive. And had I been presented the square root of x minus 4 in direct fashion as that for x plus 11, I could have said x minus 4 is greater than or equal to 0, but because x minus 4 has to be positive, we have to set this up along the lines of x minus 4 is greater than 0. And so for what we will have in the case of x, we're going to have the x is greater than 4. And looking at what we have, okay, so the number to which the inequality is centered around, okay, and that is 4. And we have the x is greater than 4, so 4 is not included. So we have a hole at the location of 4. And then we have from this, we have a ray that is going to go out to the right and running continuously to infinity. And for the domain of this function, okay, so we're going again with the values of x greater than 4. So we'll have going past 4. So we place 4 with a parenthesis around it, signifying that 4 is not included. And then we have, again, going out continuously to infinity, again, which is boundless. All right. Now, for what we have in the case of item number 3, okay, and we have in the crossover to linear equations and relations, okay, and we looked at items like the point slope form of a linear equation as well as the slope intercept equation of a line for individual situations, and then we cross over to where we have classifications of relations between lines, some of which are parallel, some perpendicular, others, okay, which you don't have either of the two. And in what we have with item number 3, okay, so we're looking at determining the slope-intercept equation of a line that is going to run parallel to 2x plus y is equal to 4, and where the parallel line is going to pass through 3, 3. Okay, and so for what we have in the third item, and we have with a given line, okay, and to be able to establish the equations for parallel and perpendicular lines, we need to know what the slopes will be. So for the given line, okay, we have 2x plus y is equal to 4. And if I determine what the slope is going to be, okay, so I'm going to have to present or rewrite this equation in terms of where we have y to be isolated. So taking 2x away from both sides, so I'm going to have that y is equal to negative 2x plus 4. So I already have the slope-intercept form of this equation, and so I have the slope is equal to negative 2, and for what we have in the case of the parallel line, again, parallel lines, okay, we're going to have the same slope. Okay, so we have that the slope is equal to negative 2. And we have the point through which the line is going to pass. Okay, so we have the ordered pair 3, 3. And I'm just going to do a little bit of color coding here. Okay, so you have for x01, y01, okay, so your x01 we have at 3. and the y1 we also have at 3. And moving forward, okay, so we have the slope and we have a point through which the parallel line passes, and moving forward and progressing toward to what we have in what is going to be the slope-intercept form of a linear equation. So we're looking through, going through the point-slope channel. Okay, so for y minus y01, okay, so that is going to be y minus 3. So we're talking about this 3. And we have is equal to the slope m, okay, which we have at -2. And we have times the quantity of x minus 3. And I'm referring to the x value from this point. Okay, so this part is the point-slope equation. Now for what we have in the case of the slope-intercept, I'm going to get this term y by itself. And right now I have y minus 3 is equal to -2x. And -2 over -3 becomes +6. And getting y by itself. And we have adding 3 to both sides. And so we're going to have that y is equal to -2x plus 9. And that is going to be the slope-intercept equation. And just looking at what we have here. Okay, so I have the slope at -2 and testing out 3, 3. So with y at 3, we have the left-hand side of the equation is at 3, and we want the right-hand side of the equation to also be at 3. So with x at 3, we have -2 times 3, which will be -6. In turn, -6 plus 9 is equal to 3. So the equation balances. And for what we have in the case of item number 4, okay, and we're looking for the slope-intercept form of the equation of the line that is going to run perpendicular to 2x minus y is equal to 4, and that is going to pass through the ordered pair 2, 7. And so we have here once again, we have for the given line, okay, so we have 2x minus y is equal to 4. Now I'm looking for the equation of the perpendicular line. And so we have in the setup, okay, if I isolate the y term, which we now have as -y, we have upon taking once again -2x away from both sides, so we have that -y is equal to -2x plus 4. And if I multiply or divide the equation by 1, I don't know if I said 1, I meant -1 if I did. Okay, so you have multiply or divide the equation by -1. So then we have a complete sign change among the terms. So -y becomes transformed to y, -2x becomes positive 2x, and 4 becomes -4. And so we have in the setup, okay, translating the given line equation to its slope-intercept equivalent. So we have that the slope m is equal to 2. Now, for the perpendicular line, remember, the slope values of lines that run perpendicular to each other are going to have an opposite sign reciprocal relation. Okay, so for the given line, the slope is 2. And if I take the opposite sign reciprocal of 2, so I'm going from a positive to a negative. And for the reciprocal of 2, okay, that is going to be 1/2. So the slope of the perpendicular line is going to be at negative 1/2. Okay. So just kind of a reminder for perpendicular lines. The product of the slope values will be at negative 1. Now the point through which this line is going to pass, again, we have at 2, 7. And so for what we have through the point slope setup, okay, so we have y minus y01 is equal to the slope m times the quantity of x minus x01. And substituting, so for y minus y01, we have y minus 7. We have m, we have at negative 1/2. And we have times the quantity of x minus 2. And we have, we're distributing, so we have negative 1/2 of x. And negative 1/2 of negative 2, negative times the negative is a positive. So we have plus 1. And we have, upon isolating the y term, so we're going to add 7 to both ends of the equation. And we have, upon getting y by itself, so we have that y is equal to negative 1/2 of x plus 8. Okay, and you can check the result here. So with testing out x of 1, y of 1 equal to 2, 7, and just filling in y of 1 for y, x of 1 for x, the left hand side of the equation is going to be at 7, and I want the right hand side to be the same result. So we have negative 1/2 of x at 2, so negative 1/2 times 2 is negative 1. Negative 1 plus 8 is also at 7. Okay. Now, in the case of what we have for the next item, and we have in the crossover to looking at once again the domain of functions. And okay, so we have for the given function, okay, no radicals in this one. And so we have f of x is equal to, okay, we have 2x plus 7 all over x squared plus 4x plus 3. And it says to determine the domain of this function. Okay. All right, so the restriction, okay, is going to come with respect to the denominator, okay, and the restriction is that we cannot have a zero-valued denominator. Okay, so here we have x squared plus 4x plus 3 cannot be equal to 0. And looking at the factors, so x squared plus 4x plus 3 factors to the quantity of x plus 3 times that of x plus 1. Okay, so the whole expression cannot be 0, and that means that the factors cannot be 0 either. So for x plus 3, if this cannot be 0, then x cannot be negative 3. if x plus 1 cannot be 0, but we also have the x cannot be negative 1. And so we have with the exclusions of interest with negative 3 and negative 1. Okay, so we have a whole on negative 3 as well as a whole on negative 1. And just looking at what we have regarding the domain, okay, from a graphing perspective. Okay, so negative 3 and negative 1 are both left out. So we have for the domain of this function. Okay, so we have for the first portion, or at the lower ends, we have going from negative infinity, approaching but not including negative 3. So negative 3 is going to be bypassed, and so we're going to have a parenthesis, and then we'll have values between but not including negative 3 and negative 1. So we have an open parenthesis, and so we put in negative 3, and we have approaching negative 1. Again, negative 1 is going to be excluded, so we have a closing parenthesis around that. And then for the final stretch, we have an open parenthesis, and this means we're going past negative 1 and heading out toward infinity. So we have two exclusions from the domain, and in the interval notation, we have three subsets in the formation. All right, so for what we have for item number 6, okay, so you have f of x equal to 2x minus 1 all over x squared minus 4. All right, so we have, in the case of the domain, so again, just like x squared plus 4x plus 3, which is in the denominator, we have x squared minus 4 now at the bottom part of the fraction, and it is now that which cannot be equal to 0. So with x squared minus 4, if this cannot be 0, well, the factors cannot be equal to 0 either. And here we have a difference of squares. We have x plus and x minus the same amount, namely 2. And with x plus 2, okay, we're going to have the exclusion from the domain to be the restricted value negative 2. And we have also if x minus 2 cannot be 0, well, we have also the x cannot be equal to 2. Okay. So we have, in a sense, we're going to have a bit of history to repeat with two distinct exclusions from the domain. Okay, and these both happen to be additive inverses. So we have negative and positive 2 excluded. Again, we have holes at the exclusion, and you have a line segment in between, and rays to the left of the smaller exclusion, and a ray to the right of the larger. And so for what we will have in the case of the domain, okay, so you have going past negative infinity, approaching but not including negative 2. We have along with those values of x. Okay, so we have going past negative 2, approaching but not including 2. And then we have those values of x, okay, which will be greater than 2. All right. Now, again, we have 2 exclusions, and in the interval notation, okay, the domain has, once again, 3 subsets in the formation. Okay. Now, for what we have in the case of the next items. Okay, so we have with number 7, okay, we're looking at determining both the slope and the slope-intercept equation of the line that runs through the points, which we have at -1, -3, and 3, 5. And so in the case of what we have with 7, so we have -1, -3, and 3, 5. Okay, now for the slope, again, you're looking at change in y with respect to change in m. So the slope, we have y of 2 minus y of 1 all over x of 2 minus x of 1. All right. And again, okay, I know that some will try to determine the slope before they, first of all, just kind of partition and separate, okay, what the first x and y and the second x and y values are going to be. Okay, and so for -1, -3, keep in mind once again that all ordered pairs are of the form xy, and since we have this ordered pair given first, we say we have x01, y01 will be respectively -1, -3, and with 3, 5 given subsequently, we say that 3 will represent x of 2 and 5 will represent the second y value. Okay, and with this information already stored, okay, so for y of 2 minus y of 1, y of 2 we have at 5, then got subtraction of y of 1, we have at -3. For x of 2 minus x of 1, x of 2 again we have at 3. Again we have subtraction. X of 1 we have at -1. And we have 5 minus -3, so this will be 5 plus 3. For 3 minus -1, we have 3 plus 1. And so we have 8 over 4, and that reduces to 2. So the value of the slope comes out to 2. Now for the slope-intercept equation, you can choose either of these 2 points for x01, y01 in the point slope setup. And if the inclination is to say that, well, because I use x01, y01 with -1, -3, I'm going to go with this. And again, that's a viable option. Let's say that if one wants to kind of sidestep from working with negatives, you can choose this ordered pair. So there's no one right way between these points. You could choose either one. And say if I were to go with 3, 5, and we'll have for the point slope equation setup. Okay, we have y minus y1 is equal to the slope m times the quantity of x minus x of 1 and for the items we have at hand. Okay, so again, we have your y1, okay, we have at 5, and your x01 in this case. So for your x01, okay, so that is going to be at 3. And again, we just determined the slope. So just filling in. Okay, so you have y minus y01. So you have y minus 5. Again, the slope m we have at 2. And we have times the quantity of x minus 3. So you have y minus 5. And for 2 times the quantity of x minus 3, this will be 2x minus 6. And we have adding 5 to both sides. So we have that y is equal to 2x minus 1. And you can go back and check the results here. Okay, so say if I have, again, y at 5 and x at 3, I want both sides to be equal to each other. So left-hand side we have y, which is 5. And I want the right-hand side to be as well. And we have a 3 representing x. We have 2 times 3 is 6. 6 minus 1 is 5. 5 is equal to 5. And if I test out -1, -3, so we have y at -3. So the left-hand side of the equation is -3. And I want the right-hand side to be as well. And we have with x at -1, we have 2 times -1 is -2. And -2 minus 1 is also -3. So it all works out. Now, for what we have in the case of item number 8, okay, and it says that we have a given function, okay, which we have in the quadratic expression, okay, whereupon we have f of x is equal to negative x squared minus x plus 4. So you have f of x equal to negative x squared minus x plus 4. Now I'm looking for f of 3. As well as f of -2. So looking at specific y values for these specified inputs. And then for the last part we have for f of x plus 4. I'm looking at what will be the resulting functional expression, okay, for the general input, which we have at x plus 4. Alright, so you have the given function f of x. You have negative x squared minus x plus 4. Let me mention now, you got the negative of x squared, and this is not going to be the same as the square of negative x. Like negative x times negative x will be positive x squared. So think of this like -1 times the square of the input. Okay, so for f of 3, so you'll be looking at like the negative of the square of 3. And we have minus x, so this will become minus 3. We have followed by the addition of 4. Okay, now 3 squared is 9. Okay, but I'm still going to be taking the opposite sign of this. So 3 squared is 9. Opposite sign, we're going to have -9. And we have again minus 3 plus 4. And we have -9 minus 3 is -12. And in turn, negative 12 plus 4 ends up at negative 8. So we have here, whenever we have x at 3, the resulting y value will be negative 8. Now for the input at negative 2, if I determine what the corresponding y value is, so we have again, so you have the opposite sign of the square of negative 2, and we're going to have the subtraction of negative 2 followed by the addition of 4. Okay, now on its own, for the square of negative 2, this is going to be a 4, but I'm still taking the opposite sign. So I got the negative of 4. Subtraction of negative 2 becomes the addition of 2. We have followed by 4, and you might see negative and positive 4 just automatically canceling each other out and leaving 2 in the middle. Or if you go in order from left to right, you have negative 4 plus 2 is negative 2, negative 2 plus 4 still comes out to 2. So whenever x is at negative 2, we have y to come out to positive 2. As for what we have in the case of x plus 4, alright, so you have the negative of the square of x plus 4. And we have followed by the subtraction of all of x plus 4, followed by the addition of 4. Okay. Now we'll just work down here. Okay, now keep in mind now the square of x plus 4. You have x plus 4 times itself. You have like x times x is x squared. And you got plus x times 4 plus 4 times x for the outside and the inside products. Whereupon we're going to have 4x plus 4x will become 8x. And 4 times 4 is going to be 16. And for the subtraction of the binomial x plus 4, so we're going to have a minus x and a minus 4. Then we have followed by the addition of 4 at the end. And you can go ahead and get those constants to go out. And we have in following through, so the negative of the square of x plus 4. So I'm going to change the signs here for this trinomial. So we're going to have negative x squared minus 8x minus 16. And having gone ahead and canceled out negative and positive 4, I have just negative x at the end. And we have finally simplifying, so we have negative x squared and negative 8x, and negative x will become negative 9x. And finally we have minus 16. So we have all three terms in the result to end up as negative expressions. So we have negative x squared minus 9x minus 16. All right. Now for what we have on the second page, okay, for the first part, and okay, so we have for this setup, okay, so we have for number 9, okay, we have piecewise defined functions. Okay, so you have for number 9, okay, so we have so we're looking for f of negative 4, f of 1/2, as well as f of 6, and also f of 15. All right, so we have in terms of which of these items to use. Okay, so we have the f of x is equal to negative 3 if x is less than 4. F of x is equal to the absolute value of x if 4 is less than or equal to x is less than 8. Then I have f of x is equal to 7 on the condition that x is greater than or equal to 8. All So we have for f of negative 4, and here we have negative 4 is less than 4. That is going to be a true statement. So have negative 4 is less than 4. And so right away we have f of negative 4, or f of any input less than 4, is going to result as negative 3. Now for f of 1/2, guess what? 1/2, like negative 4, is also less than 4. And again, for any input that is less than 4, the output is going to be negative 3. Now for what we have in the case of 6, now 6 is not less than 4, but 6 does fall between 4 and 8. So to say that 4 is less than or equal to 6, which in turn is less than 8, okay, that is going to be true. So you have this case to arise. So for any input that falls between 4 and 8 in this manner, we're going to take the input's absolute value. So with x at 6, we have f of 6 is equal to the absolute value of 6. And that in turn comes out to 6. Now for f of 15, okay, now 15 is not less than 4, nor does it fall between 4 and 8, but 15 is at least greater than 8. Okay, so here we can say that 15 is greater than or equal to 8. So this part applies. And so for any value of x that is 8 or higher, the output is just going to be the constant, which will be at 7. And so those will be the respective answers for what we have among these 4 parts. So we have f of negative 4 is equal to negative 3. And we have f of 1/2 is also at negative 3. And we have the f of 6 is equal to 6. And again, we have f of 15 is equal to 7. And for what we have in the case of item number 10, so you have another piecewise defined function, and now we're looking at f of negative 3. And we have f of 6/10, as well as f of 4.9, and also f of 5. Okay, so we have in the categories. Okay, so for negative 3, okay, we have negative 3. Now negative 3 is less than 0. So this input belongs to the x is less than 0 category, and so anything in x that is negative is going to be given the 4x minus 3 treatment. So in this case, we have 4 times negative 3 minus 3. So you have negative 12 minus 3. Negative 12 minus 3 comes out to negative 15. All right. Now for f of 0.6. Okay, now 0.6 is a small number, okay, but it is not less than 0. But we do have 0.6, okay, it does fall between 0 and 5. Whereupon we do have the statement to say that 0 is less than or equal to 0.6, which in turn is less than 5. Okay, that is going to be true. So it belongs to this category, and any input in this category is going to be given the x squared minus 1 treatment. So with 0.6, so we're going to have 0.6 squared minus 1, and for the square of 0.6 we have 0.36 minus 1, and so that is going to be at minus 0.36. 64. For what we have in the case of the input, 4.9. Okay. And now there's a substantial difference between 4.9 and 6. But like 0.6, 4.9 will belong as an input that is going to reside in the second inequality statement. So we're going to have, just like 0.6, 0 is less than or equal to 4.9, which in turn is going to be less than 5. And that is also going to be given the x squared minus 1 treatment. So 4.9 squared minus 1. So for 4.9 squared, this is going to be 24.01 minus 1. And we're going to have here, okay, this will come out to 23.01. And in the case of what we have for f of 5, okay, now 5 is not less than 0, and 5 cannot be less than itself, so that is not going to be in this particular inequality. Now 5 is not greater than itself, but it is equal to itself. So yeah, that 5 is greater than or equal to 5. And so for this piecewise defined function, for any input that is 5 or greater, it will receive the 2x plus 1 treatment. So here we'll have 2 times 5 plus 1. We have 2 times 5 is 10, and 10 plus 1 comes out to 11. So we have, when x is 5, y is equal to 11. All right. Now, in the case of what we have in crossing over to looking at operations between functions as well as their domain. Okay, so we have for numbers 11 through 16, okay, we're involving two functions, f of x and g of x. Okay, so you have f of x is equal to 2x minus 12. And g of x, okay, we have is equal to x plus 14. Okay, so for the first three parts, I'm just going to mention, okay, so again, the sum, difference, and product functions, those are going to have the same domain. Okay, now looking at the outputs. So for f plus g of x, and we have in the expanded notation case, so we're looking at f of x plus g of x. And just looking at specifying the functions in accordance to the variable expressions to which they are set equal. So for f of x, I have 2x minus 12. And for g of x, I have x plus 14. Okay. So between the functions, again, I have addition. So I have 2x minus 12. plus x was 14. And looking at combining like terms together. So you have 2x plus x is 3x. And negative 12 plus 4 is going to come out to a positive 2. All right, so that will be the result for this particular sum function for what we have given regarding f of x and g of x. And I'll get to that domain. Now for the difference function, okay, so you have f minus g of x. Okay, so we have f of x minus g of x. Okay, so f of x, again we have 2x minus 12. And have subtracting g of x. Again, g of x, we have x plus 14. Now, when I had the operation of addition separating the functions, okay, there was no sign change upon removal of the parentheses. But with the removal of parentheses this time around, the terms in g of x will be affected. So we have n following through. So we have 2x minus 12. And from g of x, x plus 14, which will be affected by the subtraction, will become negative x minus 14. And so we have 2x minus x becomes x. And negative 12 minus 14 becomes minus 26. So we have x minus 26 in the result. And for what we have in the case of the product function, so we have for f times g of x. So we're going to have f of x times g of x. So we're looking at multiplying 2x minus 12 and x plus 14 and just taking the FOIL. So we have 2x squared. Now we're going to have 2x times 14 will be 28x. Negative 12 times x is minus 12x. So if I have 28x minus 12x, I'm going to have a positive 16x in the difference. And negative 12 times 14, this will be a highly negative value, which in this case is going to be minus 168. Okay. And again, regarding the domain, okay, so the sum difference and product functions will have the same domain, and the domain will be formed by combining the restrictions, if any, of the individual functions involved. And the individual functions we have with f of x and g of x. And since both f and g of x are just expressions that do not have a fraction or an even root radical or anything else that might create a restriction, we have for both of these, okay, we have no restriction, and since there's not a restriction for, so that's just going to cascade throughout what we have for the sum difference and product functions. So you have no restriction, no restriction, and no restriction. Okay, so as long as there is no restriction, okay, this is going to mean that for the domain, of the sum difference and product functions, Okay, so for each of these, okay, so this is just going to be the set of all real numbers. Okay, so basically we had the set of all real numbers, and since we had the same result in the domain for these operations, you had the set of all real numbers in triplicate. Now, with the quotient function, okay, now we're still involving f of x and g of x, and we still have to be able to work with f of x and g of x. But again, because I have the operation of division involved, and since there's going to be a fraction, I can still have an added restriction involved, or just a whole restriction that the sum, difference, and product functions do not have at all. So for f over g of x, can I have f of x over g of x? And for f of x over g of x, so f of x, we have a 2x minus 12. And g of x, okay, we have an x plus 14. Okay, and just substituting, just filling in, turns out that the greatest common factor among the terms is only going to be 1, so there's no simplifying for what we have here, because 2x minus 12 over x plus 14, that is already in simplest form. Now regarding the domain, okay, so here we have a fraction. Now again, there are no restrictions for f of x and g of x in the context upon which they were presented. But now with g of x situated in the denominator, okay, what we have for g of x cannot be 0. So now we have the x plus 14 cannot be equal to 0. So for the restriction on this rational function, okay, we have the x cannot be negative 14. And so this is going to signify that for the domain, of f over g of x, again, think of it like a hole on negative 14. You have a ray to the left, ray to the right. So for the domain here, we have those values of x less than negative 14. Again, negative 14 is going to be bypassed. And for the rest, we will have those values of x which will be greater than negative 14. Okay. Now, for what we have in looking for domain, okay, and we have with the composition of functions. Okay, now again, the sum, difference, and product functions, you're looking at combining restrictions from, in this case, f of x and g of x. And that's again was with the sum, difference, and product functions. And the quotient function, again, because you have a fraction involved, you had the restriction that the denominator could not be equal to 0. Now, in the case of the composition of functions, again, you kind of create a dividing line here, because in the domain, you're sort of hitting the reset button. And for what we have, once again, we have with f of x, again, we have it 2x minus 12. With g of x, again, we have x plus 14. Okay, and in the case of problem 15, so we're looking at f composed with g of x. And in the notation for the compact notation, so we're looking at f of g of x So in the composition, now we're going to have the output in accordance with what is prescribed for f of x. So again, in terms of what we're going to do with g of x, so again we have f of x, f of the input is equal to 2 times the input minus 12. And now with the input at g of x, so I now have 2 times the input g of x minus 12. Okay, so 2 times g of x. So once I fill in the variable expression, so we have 2 times all of x plus 14, take away 12, so I have 2x plus 28 minus 12, and for the resulting composition, we're going to come out to 2x plus 16. Now where the domain is concerned, again, two things to focus upon. Okay, so we have with the input function, again, we have g of x okay, g of x is equal to x plus 14. Okay, and x plus 14, there's no fraction, no even root radical, so this one has no restriction. And as for the output, which is that composition itself, again we have 2x plus 16, so we have direct terms, no fraction, no even root radical. This also has no restriction. Okay, so looking at combining the restrictions, if any, of the input and output, this will define the domain of what we have for the composition involved. So between the input and output, there is no restriction at all. So this means that for the domain of f composed of g of x, this is also going to be the set of all real numbers. And in the case of what we have with number 16, okay, so I'm just reversing the order in the composition. So we have with 16, okay, so we have g composed with f of x and that is equal to g of f of x. Now before we had the output function to be in accordance with f, now it's going to be in accordance to what was prescribed for g of x. So again, g of the input equals the input plus 14. Now with the input at f of x, so g of f of x will be f of x plus 14. And f of x, we have the quantity of 2x minus 12. Followed by the addition of 14. And for what we have in this end result, okay, so that is going to come out to 2x plus 2. and for what we have in the case of the domain. Okay, so again, just looking at the input function. Again, that was at f of x equal to 2x minus 12. Again, since I have a direct expression, no fraction, no even root radical, okay, we have no restriction. And for the output, okay, so we have with 2x plus 2. So you have a direct linear expression. Okay, so this also has no restriction. So between the input and output, again, there is no restriction at all. And we have likewise, okay, for the domain of g composed with f of x, like that which we have with f composed with g of x, we still end up with a set of all real numbers. Okay, all right. Now, just taking what we have and looking only for the domain. And we'll just do it for the first 4 operations. And let's see. Okay, so for 17, okay, have f of x is equal to 3 over x minus 1. And g of x, okay, we have is equal to x over x plus 12. Okay. Now, I can go ahead and identify the restrictions. Now for f of x, now I got 3 over x minus 1, so x minus 1 cannot be 0, so x cannot be equal to 1. Now for g of x, x plus 12 cannot be 0, so x cannot be negative 12. And for what we have regarding the sum, difference, and product functions, again, we're not evaluating the expressions. We're just looking for the domain. Okay, so for the sum, difference, and product functions, so we can get at combining the restrictions. So for these, I had to be able to work with f of x, and in order to do so, x cannot be at 1. Also, I had to be able to work with g of x. So x cannot be at negative 12. And so for all 3 of these parts, again, these are going to have the same domain. And just looking at what we have in the overall picture, they got negative 12 and 1. So those are going to be left out. Okay, So for just for the domain of these, for the sum, the difference, and the product functions. Okay, so you have going from negative infinity approaching but not including negative 12. And we have bypassing negative 12. And we have approaching but not including 1. And then we have bypassing 1 and heading on out to infinity. So for parts A, B, and C, okay, that would be the domain for what we have here.